What's poppin', guys? Today we're going to take a look at another related rates example. An 8-foot ladder is leaning against a house and begins to slip down the side of the house. By the time the base is 6 feet from the house, the base is moving at 4 feet per second. How fast is the top of the ladder sliding down the wall? At what rate is theta changing at that moment? So let me start by finishing my drawing here. You can see the house on the right-hand side, the ladder is sliding down. I'm going to call the base A and the house side B, making the ladder itself C. I've labeled the angle theta, and now I'm just outlining my given information. So we know that the base is 6 feet from the house at the time that we care about. We know that it's an 8-foot ladder, and we can use Pythagorean theorem to solve for B, which is 2 root 7. dA dt represents the change in the base. That is the 4 feet per second. It's increasing, so it's positive. dB dt is what we're interested in finding here. How fast is the ladder falling? So that's our unknown. So we're solving for dB dt, and we need to set up an equation that relates all this information. I'm also going to take note of the fact that dC dt is a thing, but we will get back to exactly what dC dt is and what it represents in a little bit. So let's start by setting up an equation. We are solving for how fast the top of the ladder is sliding down the wall, which means that we need dB dt to be included. So I'll use Pythagorean theorem, as we often do with these types of problems. So we have a squared plus b squared equals c squared, and I can find the derivative using implicit. 2a dA dt plus 2b dB dt is going to be equal to 2c dC dt. And everything is in terms of dt because it's with respect to time. So let's take a look at that dC dt that I kind of put off to the side. C represents the length of the ladder. So what does dC dt represent in this context? Well, dC dt is the change in the length of the ladder. But the length of the ladder is not changing as it slides down the wall. The ladder is a fixed length, right? The ladder's length is constant. So because the ladder's length is constant and it's always 8 feet, dC dt, the change in the ladder's length, is non-existent. It's just 0, right? The length of the ladder does not change when it slides down the wall. So dC dt here is 0, which is going to make this equation a lot easier to work with, because the entire right-hand side is just going to become 0. So now I can proceed and actually substitute in all the information that we have, because now there really is just one unknown, the dB dt that we're looking for. So I have the right-hand side going to 0, and now I'm just going to substitute in everything on the left-hand side. Again, that 2 root 7 came from using Pythagorean theorem. So now you can see we have the one unknown, and now I just need to clean this up a little bit. Remember that the ladder is sliding down, which means that the length b is decreasing. So I do get a negative number for dB dt. I get roughly negative 4.5. And I am going to use negative 4.5 as the rounded answer when I do the second part of this problem. All right. So the second question is asking, at what rate is theta changing at that same moment? So they define theta as this angle that is between the base on the ground and the ladder itself. So I really like this type of question because it really requires trig, obviously, which is exciting, and we like trig. Super happy face for trig. But what's really great about it is that it really doesn't matter what trig function you use as long as you can relate some of the information that's at play here. So you could actually use essentially any trig function to figure out this answer. Let's just rewrite our given information that we have here. The a is 6 at that specific moment. The b is 2 root 7 as we calculated. C, the length of the ladder is not changing. It's 8. We know our dA dt, our dB dt, and our dC dt as well. So I'm just going to write those out. And again, I am going to use the negative 4.5 as a rounded answer here for dB dt. You could use a more precise answer if you wanted to, but it's okay to round a little bit. And our dC dt again is 0 because the ladder's length is not changing when it slides down the wall. So we need to set up an equation such that we can figure out what d theta dt is. That's really what we're interested in. At what rate is theta changing at that moment? So you can set up any trig function you want as part of your equation. I'm going to use sine. Sine is defined as opposite over hypotenuse, which in this context is b over c. And this is the equation I'm going to use. Now I just need to differentiate. The left-hand side becomes cosine theta d theta dt. On the right-hand side, we have b over c, and that means that I need to use quotient rule. Now, there is a way around using quotient rule, which I'll let you guys see if you can figure out on your own. It has to do with c being a constant, but I'm going to go ahead and use quotient rule just as a worst-case scenario. A prime b minus b prime a, all over the bottom getting squared. And now I have my equation. We are trying to solve for d theta dt, so I need to get rid of everything else that has a variable in it. Cosine is a problem here because we don't actually know what theta is, but we do know that cosine is the same thing as the adjacent divided by the hypotenuse. So you can actually replace the cosine theta with a over c, getting rid of the angle. Leave the d theta dt, and now on the right-hand side we just need to do a lot of substitution. The bottom, the denominator is 64 because c was 8. And I'm just going to plug in the other information that I have here. And remember, our dC dt is 0, so that makes that a little bit nicer. Getting back to the left-hand side, a is 6 in that moment, c is 8, so a over c is 6 over 8. The d theta dt is the thing that we're solving for. And now we just have a number on the right-hand side. I am going to leave it in terms of a fraction here because I want to try to avoid a calculator until I absolutely need it. D theta dt, we're going to do some multiplication here with fractions. It's a good time. It's a Friday night. So negative 36 over 64 times 8 over 6, multiplying by a reciprocal. Oh man, we can cancel some stuff out here. We don't even need to use a calculator still. And we end up getting some pretty nice cancellations. We end up with negative 6 over 8, which is the same thing as negative 3 over 4, which means that we get negative 0.75. So this is our d theta dt in radians. And while this is the correct answer, it is always preferred to have final answers be written in degrees when it comes to angles in real-world problems, because we can kind of grasp most values in degrees, whereas trying to interpret 0.75 radians is a little bit more tricky. So I'm just going to rewrite it as a fraction again, negative 3 over 4, and to convert back to degrees, multiply by 180 degrees divided by pi radians. That cancels out the radians unit and applies the degree unit, and we get approximately negative 43 degrees per second. So now we can really understand at what rate the angle is changing. As the ladder is sliding down the wall, at that specific moment, the angle is decreasing by 43 degrees per second.